Good morning. Welcome to our first class. Nice to see you. I hope that you are live. This is going to be our fourth partial. Science class. And this is our video class, number 1. Remember that you should take notes. We are still having quizzes every week. I believe you have a quiz tomorrow. So let's try to pay attention as much as possible and take notes. I'll be checking some things. Okay. Sorry for the delay, but I'm working on this software which I am new at. So we should all be. So we're gonna try to finish the book, even though, as you can see, I'm basically giving you reading assignments. So and for you to study, for you to make summaries, for you to make questions. The questions we're going to be, you can ask me questions through the WhatsApp group, okay? In fact, I'm going to ask, I know there's a little bit of delay between what I say and the real time, so it's just gonna be like 10 seconds delay. I'm gonna ask something. Okay, so it doesn't matter if you're not live because this is going to remain on YouTube. So let's not worry about if you're live or not. But it is important you to make me questions through the WhatsApp group. And the questions that you have, you can make them before the video. In this way, I can already have the answer ready for you. Okay? Okay. So let's see. Checking the WhatsApp right now. Okay. So as I was telling you, we're going to try to finish the book. But if we don't have the chance to finish it because we are in a difficult situation, and also because it's a lot of chapters, but I think we can do it because it's not. We're gonna go through the basics. Okay, so in this partial, we're going to be talking. It's going to be an introduction for you people. It's going to be an introduction of what we call chemistry. Okay? Chemistry is the branch of science, of the physical sciences, that studies matter, the properties of matter, and their interactions. Properties of matter and interactions. Interactions between matter. Okay. And the first, I assume that you already read the homeworks, which is from the structure of matter to metals and nonmetals. That is chapter 16 and chapter 17. This is going to be your first quiz. I'm going to make your first quiz of chapter 16 and chapter 17. Chapter 16 and chapter 17, which is the structure of matter, metals, and nonmetals. Okay, so let's begin. Let me try. Okay, maybe if I had a. Okay, so the importance here is that we can see the whiteboard. Okay, so on page 426, it's very interesting because so far we have studied physics more than chemistry, although they are very close together. If we analyze the universe, we as humans have tried to explain the universe, that is the macro universe, the big universe, and the small universe through these two sciences, physics and chemistry. As I told you before, chemistry is the branch of science, of the physical science, that studies the composition of matter, properties of matter, how matter interacts with itself. And physics studies how this matter, also how the matter interacts with the universe, but in a different way, in a sense of motion, in a sense of energy. We will be seeing energy also in chemistry, but as I told you, these two branches, physics and chemistry, they are always interacting because the physics of things depends on the chemistry of things, and the chemistry of things depends on the physics of things. That is why there's a branch called physical chemistry, which bonds these two together as the universe really is. Okay, so all of these chemistry things begin with asking ourselves a question. What are we made up of? Right? Or what are we? Right? A fundamental question. What are we? And I mean, it's a philosophical question. It begins from a philosophy of asking yourself, what is this? What is this? Are these the same things as my thoughts or no? What is happening? It's a fundamental question. And so far we know only humans have asked this question. What are we? We don't know if any animals is asking itself what he is, or what is what is this environment that surrounds it and that we interact with. So it's a fundamental question. What are we? And another question that rises from this is, what are we made up of? And even a little bit more. Let's see. What are we made up of? And why don't we ask another question? Why don't we change this we for what is everything? What is everything made up of? Everything, people. So, as you read on the atomic theory, it's a fundamental question, and this was addressed by our ancestors, the Greeks. And it's famous. I think I've told you this example before, but one of the philosophers called Democritus came up with the idea that if you would, well, there were two debates actually: Democritus versus a more famous philosopher, Aristotle. Two ideas, and I'm gonna begin with Aristotle's ideas, which was the wrong idea, which is, or maybe not, we still don't know, and that if you would have, imagine a piece of paper that you would cut with an infinitely sharp knife. So a knife so sharp that it can cut anything, the smallest thing. So Aristotle said that matter, or the things that we are made up of to answering this question, he said that you could cut something into half, right? Cut it, and then cut it also into half, and then cut this to half, and then cut this to half, and then this, and then this. You know, you get the idea, right? Cutting to halves. Cutting. So he said that you could basically cut matter infinitely. He said that there is no limit at where you can cut matter. This is the symbol for infinite. So Aristotle said that matter, you know, you can cut it forever. On the other hand, Democritus said you can cut matter a lot, but there is going to be one point or one thing that you cannot cut, and that is what he called the atom, which in Greek means uncuttable. This is Greek for uncuttable. So a little bit of Greek up here. And, well, this is where the idea of the atom comes from. It came more than 2,000 years ago. It came on the year, let's say, it doesn't say here, but it was like at least 100 years BC, you know. Or as Angel says, before the Common Era, BCE. So, this is the idea of the atom. And for a lot of time, it was actually Aristotle's idea of that you can cut infinitely something that people accepted. Now, but then, in the 1800s, you see how almost 2,000 years later from the idea of Democritus and the atom, a lot of time later, because this is the Common Era. And, well, with the scientific revolution of the Renaissance and the Enlightenment ideas also, then science, bloomed. Science exploded. And in the beginning of the 1800s, this person, John Dalton, he came up with a way to show the evidence of the existence of atoms. And what he did is basically he was making experiments, but he was counting the proportions of the amount of things, because chemistry already knew a lot of things, thanks to a non-science of the Middle Ages known as alchemy, which was a very experimental way of dealing with matter. The alchemists, maybe you have heard, they wanted to change lead, plomo, into gold, oro, but they couldn't do it. But in their experimentation, they found out a lot of things. So the alchemists, that was not a science, but it had a lot of practical science, of practical ways that led up to the creation of science. So this guy, John Dalton, he discovered that atoms really do exist. Okay? And he thought that atoms were round pieces. That they were round, like marbles. You know. So he was the first idea. He was the first person to evidence the existence of atoms by measuring the mass of different proportions of different elements. Well, the idea of elements is still not going to happen, but well, yes, they did have an idea of elements already, but they were just discovering. They discovered. John Dalton proposed some of the symbols of these elements, as you can see on page 431. So these were the earliest elements that were known already: hydrogen, oxygen, carbon, copper, nitrogen, sulfur, phosphorus. And as I was telling you, he thought that atoms were round little marbles. That's all that he could discover. Now, a few years later, 100 years later, in 1897, another scientist by the name of Joseph Thomson, he made another important discovery about the atom. He found out that atoms have two different charges. Okay? He found out that atoms have positive, but they also have a negative charge. Okay? And he proposed a model of the atom like a chocolate chip. Like a chocolate chip that the mass is positive, like the mass of the chocolate would be positive, and that the chips would be, like the chocolate chips would be the negative things. And the experiment, as we can see over here, consisted in that he would, well, it's not really that important. If you want to look at a video right now, well, it is important to understand, but what he did was basically this. Through this cathode tube, he had a positive magnet. Okay, the positive pole of a magnet, and what he did, he placed a beam of matter. He bombarded it with matter and of electrons, I think. Well, as you can see over here, yeah, the experiment is very well explained over here. So what he did is that array of electric current. Okay, it was electric current. So as we know, electric current is made up of what? Of electrons, right? So what happened here was that because the electrons were attracted to one side of the cathode tube. And why, they asked themselves. That must mean that matter must have a charge. And that is what matter really has. So, thanks to Joseph Thomson, now we know that matter has an electrical charge. That they have a positive and a negative charge. Okay? So, 100 years later from Dalton, we know this. Let's see if you have any questions right now. Okay, next. And now, only 20 years later, or less than 20 years later, on 1911, yeah, we have the next important discovery by Rutherford. And this guy Rutherford, as you can see, his experiment of the gold foil, what he did is that he bombarded a gold foil, a foil, una lámina, a very thin lamina, a very thin foil of gold. He bombarded it with alpha particles, okay? So these are particles that are positive. So he bombarded them, and he placed, as you can see in the diagram, he surrounded it with a material that could receive and make a signal if particles were passing through it. Now, what he expected it was that the particles, this is what he thought was going to happen, that all the particles will pass through. Okay? And that happened. But also, because this is what he was thinking, he thought that, let me see, I'm gonna use blue for the particles, okay? So he thought that the particles were just going to pass through, and that the gold, which I'm going to use red for the gold. So this is what he thought, that at the atomic level, this is what was going to happen. He thought that you would have gold particles, atoms, lining up, and that the positive beams would just go through them. Okay, because they were smaller than the gold atoms. Now, what really happened was, yes, they passed, but some of them also bounced in other directions. So why were they bouncing? So it seemed that what really was happening is that atoms had a lot of empty space. This is what he thought. Atoms have a lot of empty space. That means that even though sometimes they can pass through the empty space, but a small amount of times, because most of the times they pass directly, but some of the times they bounce. So, through a lot of scientific imagination and collaboration, they found out that the atom is mostly empty space. In fact, atoms are, the new model is like this. We have a nucleus, and surrounding the nucleus, we have electrons. And this would be our atom. All of this. You can see how it has changed, right? Now we have a nucleus, a positive nucleus, and negative electrons moving around. And the nucleus is so small that if you were to compare it, the size of the atom to a stadium, like Estadio Nacional, the nucleus would be the size of a football. Okay, the size of a football. So as you can see, an atom is a lot of empty space. Okay, now next was the discovery of the neutron. And the neutron was discovered by Chadwick, and I'm not going to explain how he discovered it. So now we already know that not only in the nucleus contains a positive charge, it also contains a neutral charge. So now we have three subatomic particles. We have the protons, neutrons on the nucleus, and we have the electrons moving around the nucleus, and the electrons are negative, as we have heard before. Now, the next step in the atomic model came by um, Niels Bohr. Now, I don't know the year, but Niels Bohr won the Nobel Prize in 1922. So it must be in the 1920s that Niels Bohr discovered that atoms have, so if this is the nucleus, and these are the electrons that are moving around, electrons have different energy levels. And we have seen this before when we studied light. So it was Niels Bohr that discovered that electrons have different energy levels, and that electrons can actually jump from one energy level to another. Okay, this is going to be very important for later chapters. So you can see that Bohr's model has different energy levels. Today, the modern model of the atom consists in knowing the nucleus, but thanks to another branch of science called quantum physics and quantum mechanics, quantum chemistry. No, not chemistry. Sorry. We know that the electron, you cannot know the exact position, so we don't know. We know that it doesn't have an orbit. We don't know the way that an electron is going to move around the nucleus. It's not like planets. So what we use is an electron cloud model, the last of the models, which means the possible position. Where is the probability of the electron? Okay, where is it going to be? Is it going to be near or far? So this is an electron cloud model. We don't know the position exactly, so we can only know the probability. So the more places where the cloud is more dense, that is the place where the more probable the electron is. Okay, the next part will be, we don't have too much time, but we have, let's see, we have a question. Atoms are made of protons. Yes, atoms are made of protons, electrons, and empty space. Yes. Yes. Yes, Kenzie, they are made up of protons, electrons, neutrons, and empty space. And mostly they are empty space. So we are mostly empty space. Now, let's see some of the, on section 2, the modern atom, it all works together. So it's important that you have read this. Now, I'm going to go directly to explaining the periodic table, which was perfected by this fellow Dmitry Mendeleev. Now, I'm going to explain section 2 with section 3 because a lot of section 2 can be explained. And I'm noticing that we yeah. Okay. So when you look at the periodic table, like the one you have here, we see different important things. We see the atomic number. Wait, I have to pick up something that fell off. There we go. So, In here we have different things called the atomic number, the symbol, and the atomic mass. Okay, so I'm going to explain these three things, which is important in any periodic table. Now, uh, we have different atoms, and what is an atom made up of? Protons, electrons, and neutrons. Now, what is an element? An element is substances that are made up of one kind of atom. For example, what are the different atoms? We have, on the book here, we have 109 different atoms. Today we have more atoms. We have 120 atoms, or 118, I forget. 118, I think. And what are these different elements? So I will show you what different atoms are. Different atoms consist of having different amount of protons. Okay, protons are the key. Now, hydrogen has one proton. So if you have one proton, you have hydrogen. So the number of protons is the atomic number, and the symbol is the symbol for the element. So the name is like an abbreviation of the name. Now, we also have the mass, the atomic mass. And this is where I have to explain something called isotopes. What is an isotope? So, the thing is that we're not counting the number of neutrons, but, for example, an element can have different number of neutrons, because an element is made explicitly by the number of protons it has. So, for example, if an element, if a substance has one proton and 0 neutrons, it's hydrogen. If a substance has one proton and 1 neutron, it is still hydrogen. If a substance has one proton and 2 neutrons, it is still hydrogen. But we can see that we have 3 types of hydrogen. So, the atomic mass, it tells us how many particles do you have in the nucleus. Okay? How many particles? So you have to count the number of protons, but also the number of neutrons. But because we have 3 different types of hydrogen, that means that we have to make an average. Okay? So most of the hydrogen only has one particle, okay? But some of the hydrogen has 2 particles, and some of the hydrogen has 3 particles. So we have to make an average, right? An average of the 3 types of hydrogen, and this is the average, 1.01. Okay? It has on the nucleus, it has an average of the particles that we know in the universe. This, okay? If there were only one type of hydrogen, then the atomic mass would be 1. Helium, for example. Helium has 2 protons, but it always has, most of the helium we know has 2 neutrons also. So helium is 4, as you can see, right? Almost exclusively helium is like this. The next one is lithium. That means that lithium has 3 protons. And how many? It says 6.94. That means that lithium, most of the lithium has 4 neutrons, right? Most of the lithium that exists in the universe has 4. Why? Because the atomic mass is close together to the mass number. Okay, the mass number is easy. The mass number. The mass number that you can see on page 440 over here. The mass number is of a certain particle. How many particles does it have on the nucleus? And as you can see, mass, we are giving most of the mass only to the nucleus. Why is this? Because the electrons almost don't have mass. Okay, they have the mass of the electrons is so small that they don't contribute that they don't contribute so much to the mass of matter. Okay. Error. YouTube is not receiving enough video to maintain. Okay, I hope that we're not having problems here. Okay, so this is the mass number. For example, for the most abundant type of hydrogen is 1. For helium, it's 4. For lithium, it's 7. Why? Because, for example, this lithium over here has 7 mass number. 3 protons, 4 neutrons. 7. And so on, and so on. So that is what periodic tables show us. And this will have to be our class, people, because time is running out. And I hope I'm not having problems with the streaming of this video, because I see that YouTube here is warning me something. So the quiz of tomorrow is just going to be of the first of chapter 16. Okay? So the quiz only of chapter 16. Oh, actually, forget about it. Yeah, chapter 16 and chapter 17. If you have any questions on what we see today on chapter 16 and chapter 17, and so make them through the WhatsApp. Basically, you know, the periodic table is arranged in groups. That means that each type of group has different characteristics. Okay, so we have here on page 449 a periodic table. So we have, as you can see, different groups, and you can see that most of the elements are metals: alkaline metals, alkaline earth metals, transition metals. The only ones that are non-metals are these ones. These ones are non-metals. And what is a metal? Well, it says there, right? That a type of substance that can conduct electricity, that can conduct heat, that has certain characteristics, that most of them are solid at room temperature, and they have kind of luster, que es brillo, some of them, right? And they have other characteristics in common that we should read, and if you have any questions, you should tell me about it. What makes metals metals is how their electrons behave. You see, metals have this characteristic that their electrons are shared by all of the atoms in a metal. So the electrons can move around in a substance made of metal. Let me see a substance made of metal. This fork, for example. Let me see. This fork. electrons can move around freely. They are not stuck to their individual atoms, and this is what happens to non-metals. Non-metals, their electrons stay with them. Most of the non-metals, for example, here on planet Earth, at room temperature, they are gases. We have nitrogen, oxygen, other gases, let's see, helium. All of these are called the noble gases, and we were going to be analyzing them a little bit further. They are gases. We have fluorine, which is a gas. Chlorine is a gas also. And we have some solids also, like carbon, silicon, phosphorus. And well, this group, boron, silicon, arsenic, tellurium, astatine, are called metalloids because they have a little bit characteristics of metals and they have a little bit characteristics of non-metals. So you should read also chapter 17, which is metals and non-metals. So any questions you have, please write them on WhatsApp before the quiz. Okay, I'm not gonna be so strict, and you can also use the book when you make the quiz, so there shouldn't be a problem. In here, what it says diatomic molecules on page 470, let me explain what this is, because everything else I think it's pretty easy. A diatomic molecule, for example, oxygen is a diatomic molecule. That means that oxygen, if this is the atom of oxygen, most of the oxygen we find, we don't find it in one atom only. The oxygen we breathe, we find it in two atoms. Okay? So oxygen is not found one atom by itself, and I'm going to explain this later on. For example, so this is oxygen, and we usually use the symbol O2 because that means that we have two atoms of oxygen. Nitrogen, also, nitrogen is N2 because we have two atoms of nitrogen. Another one, chlorine. Chlorine is also a gas. We find it like this. Two atoms. And we also have fluorine, another gas. We find it two atoms. Now, the noble gases, we find them individual atoms. And I will explain this on the next class. Why do we have noble gases that are found only in one atom? They are gases, but they are found only as one atom. Why? So I will explain to you this on the next class. Let's see. Yes, and I have to explain periodic table also. This is not xenon, this is xenon. I want to explain things about the periodic table, but we don't have any more time today. So please use this. I'm not going to ask for anything that is so difficult, and please your questions through the WhatsApp. Let's see if you have final questions over here. And YouTube, I don't know, WhatsApp or YouTube. Okay, so bye bye people.